Hello, in this video we will begin our discussion of the thermodynamics of chemical reactions, thermochemistry for short. We start with a simple definition of standard conditions, which no doubt you discussed in general chemistry, but there are typically some misconceptions about this. Standard conditions are defined as 1 bar pressure, and so when you see the little superscript, the little 0 superscript associated with the thermodynamic quantity, that 0 represents standard conditions. It is important that you understand that the temperature is not specified when we talk about standard conditions. There is no specific temperature. So for example, in your book you'll find enthalpies of formation, standard enthalpies of formation listed at 298 Kelvin. But please understand that 298 Kelvin is not standard conditions. We could also refer to standard conditions at 310 Kelvin. That just temperature needs to be specified. So we do not assume a specific temperature when we are talking about standard conditions. The temperature has to be specified. Alright, so we'll talk about reactions and standard reaction enthalpies. So to calculate standard reaction enthalpies, the enthalpy change for a chemical reaction, we'll typically use enthalpies of formation, which are tabulated values. Enthalpies of formation, you may recall, correspond to the enthalpy change for the reaction that generates a compound or a substance where the reactants are the constituent elements in their most stable state. So for example, for benzene, the formation reaction would be graphite, which is the most stable form of carbon at 1 bar pressure and 298 Kelvin, reacting with gaseous diatomic hydrogen to form, of course, liquid benzene at 298. So this would be the reaction corresponding to the formation of benzene. And delta H for this reaction is the enthalpy of formation of benzene at 1 bar pressure and 298 Kelvin. By this token, then, you must realize that the enthalpy of formation of any element in its most stable state is equal to 0. So the enthalpy of formation of H2, for example, is equal to 0. The enthalpy of formation of graphite under these conditions is equal to 0. It is important that you specify the particular allotrope. For example, the enthalpy of formation of graphite, the most stable form of carbon at 298 Kelvin and 1 bar, is 0, while the enthalpy of formation of diamond is not. We'll talk about that a little bit later. So when we calculate the enthalpy change for a particular reaction, we'll use these enthalpies of formation. And this equation here shows a shorthand way to deal with that. So here we have a summation where delta H naught would be the standard enthalpies of formation of the particular species in the reaction, and this quantity nu sub I corresponds to the stoichiometric coefficients, and where in this particular format the reactant coefficients are less than 0 and the product coefficients are greater than 0. So this all amounts to what you already know, what you learned in general chemistry, and that is that to calculate the enthalpy change for the reaction, we just take the enthalpies of the products multiplied by the stoichiometric coefficients minus the enthalpies of the reactants multiplied by their stoichiometric coefficients. So other ways that we can calculate enthalpy changes if we don't have the enthalpies of formation easily at hand, we can use Hess's law, which you may recall as being a product of the fact that enthalpy is a function of state. That means that enthalpy changes are independent of path. It just simply relies on the initial state and the final state. So we can divide a reaction up into steps, and we'll look at an example in a minute. Calculate the enthalpy changes for each of those steps, and then the overall enthalpy change is going to be the sum of those changes for those steps. The same thing goes for delta U, although certainly in general chemistry you talked about delta H most frequently, because most of the reactions you were looking at were occurring under conditions of constant pressure. But when we talk about internal energy, that's also important to know for these various reactions. So again, we can do the same thing if we have the internal energy changes for each step. We can add them all together, get the overall internal energy change for the reaction. We can also use bond energies to determine delta U and delta H for reactions. If we look at a table which actually has bond energies in it, we can calculate delta U, the internal energy change for a reaction, by looking at the sum of the energies of the broken bonds, which would occur on the reactants, and subtract from that the sum of the energies of the bonds that are formed in the products. You'll notice here it's important not to be confused. In this case, it's the bonds broken, the reactant bonds, minus the product bonds, which is the opposite of how we calculate delta H based on enthalpies of formation. And this is simply because when bonds are broken, energy is required. When bonds are formed, energy is released, and hence the negative sign associated with the formation. Now that would be delta U if we are calculating using bond energies. To calculate delta H, we actually have to have bond enthalpies to do these computations. And they are not the same. Even though you may have assumed this in general chemistry, a bond enthalpy is not the same as a bond energy. And again, we'll do an example in class where we take a look at this distinction. Alright, so here is a diagram where we can use Hess's law to show the reaction of the formation of ammonia from the reaction of N2 and H2 in this process. And basically we're breaking this down into several steps to calculate the overall delta H. The first step in this case would be the process of taking the N2 and H2 and associating those molecules in their constituent atoms. We have a delta H listed for that. That's step 1. Then for step 2, we have the combination of nitrogen with one hydrogen, and so this would be correspond to the formation of a bond, and this would be indicated here as negative because you'll note that the product of step 2, this particular step here, is lower in energy than we started out with, so energy is released in that step. Then we go on to step 3, which is the formation of a second bond, and so again this is the bond enthalpy associated with the second bond. And again, it is negative because a bond is formed and energy is released, as was the case for step 2. And then finally the last bond is formed in step 4. Again, enthalpy is negative here because again we get a release associated with the formation of the bond. So we just simply take those, add them all together, and we get this value of negative 45.9 kilojoules, and that would be the overall reaction enthalpy, or in fact the enthalpy of formation for ammonia. Notice of course that it's negative, which means it's exothermic, and overall we get a release of enthalpy in this process. Now if we have enthalpy changes and we want to calculate internal energy changes, of course we use the basic definition of internal energy in terms of enthalpy, or and rearrange that equation. Assuming an ideal gas, PV equals nRT here in the first step, we can make that substitution for PV in the case of an ideal gas into the second equation here. And that means that delta PV becomes delta nRT. Because it's an isothermal process, we can actually move the T and the R outside of the delta term, and so delta U is just going to be equal to delta H minus RT times delta N. That also means, of course, that's how we would calculate delta U if we had delta H. Conversely, if we had delta U and wanted to calculate delta H, we just simply note the rearrangement of this equation to do that. Of course, that assumes an ideal gas. Delta N here is going to be the change in the number of moles of gaseous substances in the reaction. We've already talked about this. This is the equation you're using in the bomb calorimetry experiment to calculate delta H for the reactions that you were examining. Now, what about the temperature dependence of reaction enthalpies? Of course, if we're using the enthalpies of formation given in our text, we're going to be calculating reaction enthalpy at 298 Kelvin. What if we want to know the reaction enthalpy at, say, 320 Kelvin? How do we do that? Do we assume that delta H for a reaction is independent of temperature? Well, on occasion we will if the temperature change is small enough. But we should never make assumptions like that if we don't have to. And so we have a nice little relationship here that's easily derived. It's derived in your text. It shows a relationship between delta H at some unknown temperature T to delta H at 298 Kelvin, for which we have tabulated values that would allow us to calculate. And it simply involves integration. Of course, it involves integration. Doesn't everything involve integration? I think you've learned that by now. Where in the integral, we have this term delta Cp. And delta Cp takes on the same meaning as delta H and delta U, and that it's simply the heat capacities of the products multiplied by their stoichiometric coefficients minus the heat capacities of the reactants multiplied by their stoichiometric coefficients. We have the same thing here. So we are going to have the change in heat capacity that occurs during the reaction here in the integral. Now, if we assume, again, that delta Cp is independent of temperature, and over a small temperature range, that's not a bad assumption, then this becomes an easy equation to evaluate, because the delta Cp will come outside the integral, and we're just left with integrating dt, which just then becomes delta T in this circumstance. So in that case, it's a relatively easy computation. Now, if we have a large temperature range, we may not want to assume that the delta Cp value is constant. And so in that case, we actually have to take into account the temperature dependence of the heat capacity. And we may have equations that allow us to do that. They can take on several forms. For example, this particular equation here shows Cp as a power series dependence on temperature for any given substance. But what we'd have to do is have a table that lists the values associated with each of the reactants and products here associated with that, and that means we need to find the A terms and the B terms, etc. This is something we will have to do if we have a very large temperature range and we want to calculate delta H at that elevated temperature. So we'll do some examples where we look at that temperature dependence later on. At this point ends our discussion of the basics of thermochemistry and the calculation of enthalpy changes and internal energy changes associated with chemical reactions. In our next video, we'll move on to talk about entropy, introduce the definition of entropy, and discuss how we calculate entropy changes for various physical and chemical processes. Stay tuned.